All right, hello, I'm Conrad Zimmerman, and today I'll be talking about sound gradual verification with symbolic execution. This is some work that I did in collaboration with Jenna, DiVincenzo, and Jonathan Aldrich. But first, let's talk about Wile E. Coyote. As you might know, Wile E. Coyote spends a lot of time thinking about Roadrunner, specifically how he can catch Roadrunner. But all of his plans end very badly for him and not for Roadrunner. So one day, Wile E. gets an idea. He should use verification. That way his plan can't fail. But Wile E., he doesn't know separation logic or abstract predicates very well. So he can't figure out how to use static verification. But Wile E. finds the perfect solution, gradual verification. Gradual verification allows Wile E. to incrementally build specifications and get feedback on their behavior, learning new specification constructs as necessary. So this time he wants to trap Roadrunner by blowing up a bridge just as Roadrunner is about to cross. So he writes the software for the detonator and verifies it using Gradual C0, the first and so far only gradual verifier. Verification passes, so now he just sits by and waits for Roadrunner. Roadrunner approaches and runs by without triggering any detonation. So now Wile E. wonders, how did Roadrunner get away this time? This story, it actually could have happened if Wile E. used the previous version of the Gradual C0 verifier. Now you've probably recognized by now that this is a pretty classic soundness problem. But how do we ensure soundness? To complicate things further, our verifier Gradual C0 is based on the Viper verifier and specifically its symbolic execution engine. Other verifiers such as Prussian Vercors are also based on Viper. But up to this point, at least to my knowledge, we did not have any formal soundness result or even statement for any of these tools. So I'll go over several problems that need addressed in order to formally state and prove soundness of our gradual verifier, including the formalization of symbolic execution, static verification, and dynamic verification. As I described, there previously was an unsoundness issue in Gradual C0 that we discovered through this work, which obviously needs addressed in order to ensure soundness. So for each of these areas, I'll talk about how we address the problem in question, and we'll start with symbolic execution. So as you might know, symbolic execution simulates dynamic execution and forms the basis for our static verifier, as I said. But dynamic execution often branches. So in order to prove soundness, we must prove that the verifier explores every state, and furthermore, that all of the states that it does explore are sound. We've used what we call non-deterministic rules to give an operational semantics for symbolic execution. Here we're using the word non-deterministic in the sense of like a non-deterministic automaton or Turing machine. So for example, to execute an if statement, we can evaluate this conditional expression to some symbolic value t, and then using a state where t holds, in other words, where the conditional is true, execution of the if statement transitions to the then clause. But that only covers one possible branch, so we have another rule, where we evaluate this conditional as before, and using another state where not t holds, in other words, where the conditional is false, execution transitions to the else clause. So in this way, we've specified two ways to symbolically execute the same if statement, which corresponds to the two possible dynamic execution paths. This is similar to an existing formalization of a symbolic type checker, actually, by Q et al., but we extend it to include execution of loops and other constructs. So now let's move on to static verification. As I mentioned previously, our gradual verifier is based on Viper. And so we've formalized the core subset of the symbolic execution backend for Viper that's used by our gradual verifier. I won't discuss the exact formalization, go see our paper for that, but I'll show how we statically verify Wile E.'s code. So we'll start with his catch Roadrunner method that he wrote, which takes a world parameter. So we add this to our verifier state, but now we don't know at verification time what value this will be. So we represent its value with an abstract symbolic value, which we name 1 here, in brackets to distinguish it from the natural numbers. But we have a precondition, specifically a predicate instance, representing the well-formedness of this world. So we can also just add this to our verifier state, and now we're ready to symbolically execute the body of the method. First, we allocate a detonator instance, which we add to the symbolic state, and we represent its value with a new symbolic value, which we call 2. But this instance also contains two fields, armed and detonated, which are initialized to their default values of false. But then we set armed to true, and we update our verifier state. Now we call install detonator. If we look at its signature, we see that it requires this instance of the well-formed world predicate. But we have this in our verifier state. So we can consume this predicate from the state. But now the post condition gives us this exact predicate back, or an equivalent one back, and we add this to our verifier state. Since after the method returns, we know we will have this predicate again. So next, Wiley wants to trigger detonation by calling the detonate method. But its precondition requires access to the detonated field. This specification here is an accessibility predicate, and this specifies that the detonated field is contained in the method's frame. In other words, in the set of heap locations that it's allowed to modify. So in other words, this field might be modified during execution of this method. So we must remove it from the verifier state. But now the post condition ensures that access is returned, so we add this back to our verifier state. But now we don't know what its value will be when it returns, and so we represent this value with a new symbolic value, which we call 3. But the post condition consists of two parts, joined by this separating conjunction. And the separating conjunction, as we use it here, is part of the logic of implicit dynamic frames. But if you don't know anything about that, just treat this as an and you'll be fine for this talk. The second part specifies that if armed is true, then the detonated field will be true. So whenever we evaluate this armed value against our verifier state, we can trace this back and see that it must be true. Therefore, the then clause holds. So if we look at that, this states that the detonated field will be true. So we can evaluate this against our verifier state, and this shows us that the symbolic value 3 must be true. So we can just add this to our state. Now we're done with the detonate method call, but we have more to do. Wiley wants to verify that the detonator actually went off. So he adds an assertion, which is statically verified that the detonator was indeed triggered, and always will be for any run of this program. So we evaluate this expression against our verifier state, and we find that it's true. So the assertion is going to hold. Finally, we conclude verification by verifying the post condition, which involves consuming the well-formed world predicate instance. So now we've successfully verified this method. But now, if we spent all this time verifying Wiley's code, why did Roadrunner get away? Is it because Bugs Bunny is in his computer? Well, there's at least one other explanation, and that has to do with a combination of several things underpinning gradual verification. So gradual verification, in a very short nutshell, allows incremental development of specifications by allowing explicitly partial specifications. Now, that's a lot of words, so what does it look like? Well, we'll get into that, but partial specifications signal to the verifier to make assumptions where necessary to complete the proof. However, these assumptions are then checked at runtime. So we have to formalize this interaction, and to formalize the interaction between the static side and the dynamic side, we define what we call runtime checks and valuations. So one of these partial specifications is here in the header file that Wiley received from Acme with his detonator kit. So the body of this well-formed world predicate is just question mark and true. In gradual verification, question mark can represent any formula that is consistent with the rest of the formula. For example, maybe this question mark represents an assumption that Roadrunner is always going to be in New Mexico. But it could represent any possible satisfiable formula. This alone, though, should not allow unsoundness, because we should catch those errors whenever we actually run the program. And hopefully Wiley tested it maybe a little bit at least. So what happened here? So if we go further, let's just look at this method, install detonator, that Wiley's code called. And you might first notice the fold and unfold statements. These provide information to the static verifier, but they're ignored at runtime. But there is a problem here. This method unarms the detonator, which definitely did not turn up in our verification before. So how did this pass verification? Well, let's look at verification. First, we begin with a well-formed world predicate instance. We include this in our verifier state. Unfolding this predicate exchanges the predicate instance for the body, which simply adds question mark to the verifier state. This indicates that there's a partial specification in the context, and therefore the verifier can assume things and then check those at runtime. So now when assigning to the armed field, even though we don't necessarily statically know that we have access to it, we can optimistically assume that we can access it, and we add this to our verifier state. But now in order to ensure soundness, we need to add a runtime check that validates our assumption that we made. But you might notice here, there's a symbolic value in the runtime check. What does that mean at runtime? How do we even check that at runtime? Well, in our formalism, we relate a verifier state with a runtime state with a valuation function, which is a partial function that maps symbolic values to the values at runtime. And using evaluation, the model's relation indicates that the corresponding runtime values exist and satisfy invariants such as separation. So now we can formally define semantics for runtime checks and actually assert them against our runtime state. So this allows us to precisely specify semantics for runtime checks without actually worrying about the complex source code transformations necessary to actually rewrite the program to do the checking. So in our example, the runtime check shown here is actually equivalent to the assertion that we can access and modify the armed field as we might expect. And the rest of the verification is unimportant, but it does succeed. So in conclusion, this method will succeed as long as it's given access at runtime to the armed field. And note that this actually requires a gradually verified program to keep track of the accessible heap locations at runtime and pass this set of heap locations in a callees frame when you call a method, at least wherever runtime checks are possible. There's some optimizations that you can do to get around this. But now we've verified two methods, and we still haven't seen where unsoundness can arise. But instead, the interaction between these two methods actually creates this unsoundness. So returning to Wiley's code, during verification, you might remember we assumed that the install detonator, in fact, it was specified that it only consumed the well-formed world predicate. But remember, the predicate body includes question mark, and this could represent any formula or any permission. Therefore, a naive gradual verifier would optimistically pass all the permissions that it has at runtime, because we don't know what permissions this method is going to need. So it would pass all the permissions that the caller catch roadrunner has whenever calling this method. But if we look at this, if this question mark is allowed to represent access to the armed field, this is actually inconsistent, since we would have two separate instances of ownership of this armed field, one in the predicate body and one in the verifier state. This violates the normal separation invariant that we assume during verification. We have to preserve separation between these things. And so to fix this, one possible fix is by making static verification more conservative, somehow removing one of these overlapping permissions. But since the case I've described only arises with inconsistent assumptions, we instead change the dynamic semantics by defining what we call an exclusion frame. Since only the well-formed world predicate is consumed during the call, and the verifier state retains ownership of these armed and detonated fields, these fields are included in the exclusion frame, and therefore not passed to the install detonator method. So now whenever we execute it, it won't be able to assert this runtime check, and it will show an error. And this reflects the fact that this predicate is at a point before the detonator is allocated, and therefore, if we have that assumption, the specifications and assumptions are somehow inconsistent. So in conclusion, our paper proves the soundness of gradual C0 with these modifications. Basically, symbolic execution, gradual verification, and runtime checks all imply both safe execution and that all your specifications are satisfied. Yeah, I'll just flip through that for sake of time. So we've done all this, and we have a few more things, including verifying while loops, other approaches to fixing this unsoundness. We define dynamic semantics for our language, And we finally give a proof of soundness with respect to those semantics, and we discuss future applications of this. So one final note, I'm applying to PhD programs. I might have even applied to your institution, so happy to talk more about that offline. Thank you.
Questions from the audience? So I have a question while the audience thinks. How significant is the performance difference between using the symbolic execution and not? Do you know?
Well, okay, so a few things to that. One is that we only have implemented a gradual verification using symbolic execution. We think it makes it more predictable to use symbolic execution. We don't have any other implementation to evaluate it against, so I guess that is sort of up in the air. Yeah.
Do you maybe have a sense of how many checks are removed? Like, is it...
So that's done in another paper, which you can find a preprint of. Jenna is a primary author of that paper.
Okay.
But yeah, so we do a full evaluation there.
Okay,
yeah.
Great, thank you.
Thank you for a very nice presentation. Just to be sure I understand, using this technique with the gradual thing where it fails, it tries to access the armed variable, what means in practice is that when the Roadrunner runs it, he'll just get this error and still the Roadrunner will escape. So that other invariant is preserved.
Yes, right. Yes. So under these circumstances, Wiley would not know it until he actually runs the program. And then Roadrunner would, yes, if this was the first time that he's testing it, Roadrunner gets away. Sad, but at least Wiley knows.
But it will tell him that the Roadrunner got away.
Yes.
Hey, nice talk. Don't mean anything bad by this, but was the previous version also proved sound?
No. So like I said before, the tools that we ended up formalizing, or at least parts of them, those did not have any formal statement of soundness. So gradual C0 is the first implementation. There was previously a theory of gradual verification that was developed with abstract predicates, and proven sound, but that used a completely different reasoning strategy, and also the proof of soundness is somewhat less substantial because it actually checks everything at runtime and didn't have this separation of the calculated runtime checks versus the